Hey guys, today we're going to be going over standard 8.PS4, and that is waves and their applications in technologies for information transfer. And that's broken down into three parts. We're going to develop and use models to represent the basic properties of waves, including frequency, amplitude, wavelength, and speed. We're also going to compare and contrast mechanical waves and electromagnetic waves based on refraction, reflection, transmission, absorption, and their behavior through a vacuum and or various media. And then finally, we're going to evaluate the role that waves play in different communication systems. Now, I know the first standard is going to be pretty familiar to you, is talking about frequency, amplitude, wavelength, and speed. But when we start talking about transmission, absorption, and behavior through a vacuum, that may get a little tougher. But the first thing we're going to do is go over the first PowerPoint over waves, and we will begin. All right, when we start talking about waves, we're talking about how to measure them, and they are measured with wavelength, frequency, hertz, and speed. And so as we talk about those, we'll break them down individually. Wavelength is nothing but the distance between two corresponding parts of a wave. Now, a lot of times what you do in class, you'll draw your wave, and then you'll measure from the top of the wave to the top of the next wave. But the fact that it says corresponding parts means that we could measure the bottom part of the wave to the bottom part of the wave, known as the trough. So you could do either way, or you could find any particular place on that wave and go to a spot on the next wave that looks like it and measure that distance, and it's still going to be wavelength. Then the frequency is the number of waves that pass a given point in a certain amount of time. Obviously, the faster the waves are traveling as far as how often they go by, that's called frequency. And hertz is what is used, that's the measurement for frequency. And that's the number of waves per second. So you can count 1,001, 1,002, and each second, however many waves have gone by, that's going to be the hertz. And then the speed is how far the wave travels in a given amount of time. So if the wave can really travel there in a hurry, then that's going to be considered speed. Talking about types of waves, we first need to know what a wave is. A wave is the disturbance, any disturbance, involving the transfer of energy from place to place. Now you could have sound waves, you could have different kind of waves, but if they're carrying energy and transferring it from one place to another, that is going to be by a wave. You have mechanical waves, and these require a medium to travel. In other words, they're going to have to be bumping through particles of some form. They can go through the atmosphere, where the particles are farther apart. They can go through liquids, or they can go through a solid. And I think we had talked in an earlier video that the closer the particles are together, or the denser the particles are, then the waves are going to be able to travel that much faster through those because the communication from particle to particle does not take much time. We have transverse waves, and these are waves that vibrate the medium at right angles or perpendicular to the direction in which the waves travel. When we talk about transverse waves, I believe in class we used a rope, and I believe Caleb was on one end in one class, and I think Luis in another one. But we would rock the rope up and down, and you could notice that a motion, up and down motion, would create a wave, and then that along that rope, and then that, or a slinky, a long uh, coiled wire. But as you did it, you noticed that the wave would begin to develop crests and troughs as it went, and it was carrying energy that way. And then longitudinal waves, they vibrate the medium in the same direction in which the wave travels. This is best exemplified by the slinky. I think we had a slinky, and as you would give energy in increments to that, then you could see sections of that energy going down that longitudinal wave or going down that slinky. And so in that situation, the medium is being vibrated in the same direction that the wave is traveling. Remember, in transverse, when we move up and down, the waves go out at a right angle. And then on the slinky or the longitudinal wave, then when we gave energy on one end of it, as we applied energy in one direction, the wave traveled in that exact same direction. And then finally, there are surface waves, and this is a combination of transverse and longitudinal waves that travel along the surface that separates the two mediums. If you think about uh, waves in an ocean or in a pool of water, uh, this is a surface wave. A lot of times, things will just rise up and then go back down. They're not really carried in one direction. They kind of go up and then they kind of make a little circular pattern, but then they pretty much come to rest at the same place. But anyway, the main difference there you need to know is that the transverse waves vibrate at right angles, and longitudinal waves vibrate in the same direction that the wave travels. And then finally, surface waves are a combination of the two. A transverse wave has certain characteristics. Now, keep in mind, these are the waves that we have moved up and down, and then the wave is traveling at a right angle. The wave is going to have a high point, and that high point is called a crest, and I believe all of you know that. And then the low point of the wave is called the trough. And then the amplitude is the maximum distance that the medium vibrates from the rest position. Now, this is not the distance from the trough or the lowest point to the highest point. This is taking into consideration that the medium is just laying level, and then when the wave starts, it's going to have a high and low point. So the measurement would be from its resting position to the high point of the wave. For a longitudinal wave, remember this was exemplified by the slinky, you are going to have a compression, and this is an area where the coils are close together. And then rarefaction is the area where the coils are spread apart. If you think about when we were doing the slinky, you could see little sections that would go down the slinky where they would be compressed together. And then the faster you would do them, you could see the different compressions as they moved along. And then the area where it was not close together is called the rarefaction. And then the amplitude of this particular wave measures, it's a measure of how compressed or rarefied the medium becomes. So if there is a really thick compression right there, you're going to know that it has a lot of amplitude. Now, those terms were pretty cut and dried, but now we're going to start going into a little more difficult vocabulary. You are probably familiar with several of these, but we do want to go back over them as well, as they do get a little bit tougher. The first one is reflection. And this is when a wave hits a surface and any part of the wave that cannot pass through the surface bounces back. We see this every morning when you look into the mirror. You see the light bouncing back to our eyes because it cannot penetrate that particular substance. If a wave hits something solid and bounces back, that is a reflection. And the law of reflection states that the angle of incidence equals the angle of reflection. In other words, if a wave hits at a 45-degree angle, that's going to be the angle of incidence. And then it's going to bounce off at a 45-degree angle as well. If it hits at a 90-degree angle, it's going to bounce back at a 90-degree angle. So those are always going to be the same. And then this says to draw and label this, but we are going to bypass that part for right now. And then we have refraction. Now, talking about refraction and the next vocabulary word, diffraction, they have some similarities, but they do have some contrasting areas, and so you need to really pay attention to these. Refraction is the bending of waves due to a change in speed, and the reason that the speed will change is because it's going through a different medium. Waves will travel in a straight line, except when they meet a new medium at an angle. One side of the wave changes speed before the other. think about this. I believe the way we talked about it in class was if you were roller skating and you were on pavement and you were going straight into the grass, both of your skates are going to slow down at the same time. You're going to hit it, you're going to slow down, and probably, if you're like me, you'll end up falling. Another situation would be if you were hitting that same grass at an angle. If you were going at an angle, then one of your roller skates will hit before the other will, and you're going to turn. And that's the same thing that happens with waves. You go from a smooth concrete over onto a grassy area. One side's going to slow down, and then you're going to bend or turn. And this is called refraction. And it's important to know that this is because it's going through a new medium at an angle. And that's when you're going to have that wave bent. A lot of you have seen that where you put a straw into a glass, and then it looks like the straw is not in a straight line, and that's just because the light waves are changing at a different speed going through the air as opposed to going through the liquid. And waves do not always bend when entering a new medium. Sometimes they do, but sometimes they don't. But then diffraction is when a wave moves around a barrier and through an opening in a barrier. Now, think about this. If there is a rock in the middle of a little pool of water, as the wave goes toward it, the waves are going to bend around it or going to wrap around it, but they're not speeding up or they're not slowing down. They are just bending. And this is diffraction. And so this is important to know. Refraction is going to be really important when we talk about the electromagnetic spectrum, and we will be doing that in an upcoming video. Okay, next we're going to talk about wave interference. And I think all of us know what interference means. I think in football, if someone's going out for a pass and the defender gets in the way before the ball gets there, everyone hollers, interference, interference. And that's just when two things have met, there's going to be an interaction that takes place. And that's the same thing that happens with waves. And there are two types of interference. There is constructive interference and destructive interference. Think about two waves coming toward each other. As the waves are coming together, if the two crests hit, then there's going to be a building up. It's going to be built or constructed. Think about that. There's going to be constructive interference. And that's when waves combine to form a wave with a larger amplitude than any individual wave's amplitude. So remember, amplitude is the distance from the resting position to the crest. So when two crests meet, common sense will tell you that that wave is going to then get bigger. On the other hand, if a crest of one happens to meet a trough of the other, you can just imagine that it's going to knock the other one down. If you have two players running at each other and one is going high and one's going low, the one going low would knock the one that's up in the air down, and it's going to be destructive interference. And this is crest meeting a trough. So remember, when two crests meet, they are going to be built up higher. They are going to be constructed or constructive interference. Whereas if the crest meets a trough, it's going to knock the crest down, and so it's going to be destroyed. In essence, it's going to be destructive interference. And finally, we'll talk about standing waves. Now, when two waves meet and the two crests come together, that's going to be constructive. And then if a crest meets a trough, it's going to be destructive. But there is a situation where the two waves can match and meet each other so seamlessly that the wave appears to be standing still. Even though it has two waves interfering as they go through each other, the two waves are traveling in opposite directions, but they match so perfectly that it looks like the wave is standing still. If by chance a crest is knocked down by a trough and there is zero amplitude, meaning that there is no crest above the resting point, this is going to be called a node. And then anything else is an antinode, where points produced by constructive interference where the amplitude is greater than zero and are at a maximum, and that's going to be antinodes. And they're always halfway between two nodes. In other words, they're always going to be between two points or two resting points, two troughs of that particular wave. And then the last word is resonance. And this is an increase in the amplitude of a vibration that occurs when external vibrations match an object's natural frequency. You might have heard of the term resonance, something resonating or really being very, very clear. That's because the amplitude of that vibration is just even getting that much better, and it's found its natural frequency really feels good. Anyway, this is the end of part one on the waves. We basically talked about the mechanical waves. And remember, there are two types. Well, actually three, but two main types, and those are the transverse and the longitudinal waves. And then there are surface waves as well. And we'll be going on to the next section, and we'll learn a little bit more. Anyway, thank you for watching this, and hopefully this served as a good review for you as you prepare for other lessons. Thanks.